Assalamualaikum and good morning everyone. I am Izan Zafri and me and my other two group members from the Tulfayana and Nur Izzah Hazia will be presenting our research proposal on the synthesis and characterization of molecular imprinting polymer for the removal of metal red. This is the outline of our presentation. So let's start. Color is a major part of our lives. We use it and need it for many purposes. For clothing, color is needed to show variety. In arts and paintings, color is the most important element. Color is also added to some food and drinks to associate certain colors with flavors. These colors come from a compound called dye. Dye is a compound used to impart color to the applied substance. The application of dyes includes its use in textiles, paints, cosmetics, pharmaceuticals, and printing industries. Dyes can be divided into two different groups, which are chemical structure and their method of application. There are six classes of dyes according to chemical structures. Let's focus on azo dyes. This is the general structure of azo dyes and it contains one nitrogen-nitrogen double bond, which we call the azo group. The azo group is a chromophore group that is responsible for giving the color of the dye. The azo group is attached to two other groups, which is denoted by R and R prime, of which at least one, but usually both are being aryl. Azo dyes are the most widely used dyes and represent over 60% of the total dyes. In industries, azo dyes make up 70% of dyes used, making them the most important chemical class of dyes. And textile industry usually contribute more to the percentage. However, as successful as the textile industry is, these dyes are responsible for water pollution. During the dyeing process, these dyes are released into environments like rivers, lakes, and seas. One example of azo dyes released to water sources is methyl red, and this is the structure of methyl red. This is what happens when dyes are released into the environments. The rivers appear turbid, brightly colored, and filthy, which destroys the beauty of the ecosystem. The dye is also toxic, carcinogenic, and has a low biodegradability. This will interfere with the photosynthetic activity of the underwater plants and microorganisms to produce oxygen. There are many methods to treat this dye effluents. The adsorption process is usually employed because it is cost-effective and simplest to conduct. Many absorbents can be used in the adsorption process, and one of them is molecularly imprinted polymer or MIP. Molecularly imprinted polymers or MIPs are polymeric materials that are produced using the molecular imprinting technique. These polymers are formed around a specific target or template and leave an imprint or what we call template-shaped cavities on their structure. These cavities are highly specific and can be used for molecular recognition. The designing of MIPs depend on these three components: template, functional monomers, and cross-linkers. A molecular imprinting method is based on the polymerization of a functional monomer and a cross-linker around a template molecule. At first, a precomplex is formed between a template molecule and a functional monomer, and then the polymerization is carried out around the precomplex with initiator and cross-linker addition. And finally, the template molecule is removed to generate a three-dimensional cavities for specific recognition.
The removals of dye have been accomplished by several techniques such as absorption, coagulations, flocculations, ozonations, oxidations, and membrane technology. However, some techniques are too costly, require complicated operations, and are less efficient for removing dyes. MIP is used as an absorbent in adsorption process has been proven to be more effective than other methods. Researchers are currently developing MIP to be used as absorbent in removing dye and studying its potential use in wastewater treatment. Several studies have proved that MIP are ideal and cost-friendly polymeric materials for dye removals. Therefore, this study will be conducted to synthesize and characterize the MIP for the removals of methyl red. MIP are ideal polymeric absorbents that can overcome the limitations of the mentioned technique. MIP have incredible features such as a highly selective, excellent absorption performance, and can be used repeatedly. Next, we will talk about the objective of this research is to synthesize, characterize, and evaluate the efficiency of MIP to absorb methyl red dyes. The characterizations of the synthesis MIP will be confirmed by using the Fourier transform infrared analysis, thermogravimetric analysis, scanning electron microscopy, and brown-hour emitter. Meanwhile, the removal's efficiency of methyl red by the MIP will be evaluated by using the UV-Vis spectroscopy.
To synthesize of methyl red MIP, a 0.1 millimole of MR solution will be added into a porogenic solvent containing a mixture of 10 ml of dimethyl sulfoxide and 65 ml of acetonitrile in a 250 ml conical flask. The dye will be completely dissolved in porogen by sonication before adding 4.00 millimole of methaclarate to the conical flask as a functional monomer, followed by 20 millimole of ethylene glycol dimethacrylate as a cross-linking monomer. The polymerization initiates a 0.030 gram of azobisisobutynitrile G-nitron AIBM will be added to initiate the free radical polymerization process. After that, the mixture will be dissolved using a sonicator for 10 minutes. Then, nitrogen gas will be used to push the mixture for 15 minutes. The mixture in the conical flask will be sealed and allowed to polymerize for 6 hours at 60 degrees Celsius, then 2 hours at 80 degrees Celsius. The generated polymer particle will be filtered by using a vacuum filtering assembly. On the same condition and process as for the MR-MIP ratio, NIP as a control will be synthesized with the MR template molecule omitted from the polymerization process. So the polymer microsphere obtained will be washed with methanol or acetic acid mixture for 15 minutes at 250 rpm using an orbital shaker, and then will be filtered to the template-free MIPs. The same procedure, which is washing and filtration, will be repeated until the UV visible spectrophotometer cannot detect MR in the liquid. Lastly, the polymer microsphere will be washed with pure methanol to remove acetic acid and then dried for 24 hours in the open air. MIPs that have been completely washed and dry will be stored in glass fields labels after wash. For the method characterization of the MR-MIP, the synthesized MR-MIP and NIP will be characterized by using the FTIR spectroscopy. At room temperature, they will incubated for more than 24 hours with silica gel to eliminate any remaining water before being analyzed. Potassium bromide discs of the MIP and the NIP will be prepared, and their spectra will be recorded at 4000 to 400. A scanning electron microscope SEM will be used to obtain electron micrograph to evaluate the morphology and surface structure. All the sample will be analyzed on a stub of aluminum coated under a vacuum with a thin gold layer. The thermal analysis will be carried out using the TGA instrument. The sample will be analyzed at a temperature ranging from 30 to 900 degrees Celsius at a heating rate of 10 degrees Celsius per minute. Multi-point Brunner emits Taylor BET by nitrogen adsorption and desorption isotope will be used to determine the surface area and pore size at 77 Kelvin. The PET equation can be used to determine the specific surface area. For the method for batch binding assay, ring binding assay, 20 ppm of standard MR solution will be added into the 250 conical flask filled with 0.5 gram of MR-MIP polymer samples. The conical flask will be agitated on an orbital shaker at 150 rpm for 6 hours continuously. The sample will be collected into a glass vials at every 30 minutes time interval. The collected sample will then be centrifuged at 4000 rpm for 10 minutes. Batch binding for NP will be performed in the same technique as for MR-MIPs. The UV visible spectrophotometer will be lambda maximum of standard MR at 520 nanometer will be used. Thus, the absorbance of the extracted sample will be measured at lambda maximum. The extraction efficiency of the sample will be calculated using the extraction efficiency formula. The expected outcome for this study is it is expected that MIP will be synthesized and characterized successfully. It is also expected that the synthesized MIP will be able to remove metal rate with high efficiency by the adsorption process. For the work plan, we have working for 1 year to finish this research proposal, which is we started on October 2022 and finished it on September 2023. For the first 2 months, we have prepared the procurements of materials, and for the next 4 months, we have synthesized and characterized the MR-MIP, and we have spent 2 months for batch binding assay, and 3 months for evaluate the efficiency of the MR-MIP. And the last month of this research proposal, which is on September 2023, we have submit the report and we have the oral presentation.